What up, guys? It's your boy coming at you in 4K. We're going to talk about projectile motion really briefly. The secret to projectile motion, whenever you have a problem, is to draw the trajectory. So depending on what your trajectory is going to depend on how you're going to solve this problem. The three main cases that we have are we have the horizontally launched projectile, we have the ground to ground or height to same height projectile, then we have the launched from an angle where it lands lower. Of the three different cases, these are the two most common types of projectiles. For case number one, a horizontally launched projectile. That is the big hint for you that the projectile is launched at an angle that is parallel to the ground. If it's launched at an angle that's parallel to the ground, then that means our launch angle equals 0. If our launch angle equals 0, when we find the components of velocity, where we have initial velocity in the x direction and initial velocity in the y direction, v naught cosine theta. Cosine theta, if theta is 0, equals 1. So that means our initial velocity in the x direction is the same exact thing as our initial velocity. Meanwhile, in the y direction, our initial velocity times sine theta, sine of 0 is 0. So there is 0 vertical component of our velocity. The big key or secret or tip, whatever you want to call it, is that if you need to find time, and a lot of times you need to find time, look for time in the y direction. What does that mean? That means we have to keep our x and y stuff separately, completely separate. When we do that, we want to look for time in the y direction. In the y direction, in case number one, several things are going to be given to us. Maybe we don't recognize it, maybe we do. But we have initial velocity in the y equals 0. We know our acceleration in the y equals negative 10. And we know that that's it. We don't have anything else. We might know the starting height. Our starting height if we're on a table and a projectile is launched this way, or we're standing on top of a building and we throw a football, whatever the case is, we'll know our starting height. That'll be given to us in the problem. So if it's like 10 meters or whatever. Our starting height is given to us. That means our final height will equal 0 because we're going to hit the ground. Meanwhile, in the x direction, we know the initial velocity in the x direction just equals our initial velocity. We've proved that already. And that's it. That's the only piece of information given to us. The thing that ties x and y together is time. The time is going to always be the same. Remember, the bullet fired versus the bullet dropped from the same height will hit the ground at exactly the same time. On to case 2. With case 2, we have a projectile launched from some height and it returns to that exact same height. We always want to draw our trajectories because when we draw this trajectory, we recognize that it's parabolic in nature, and we love parabolas because they're symmetrical. That means we can cut it in half, and whatever happens on the left, there's a mirror image that's also going to happen on the right. We can use that to our advantage by stopping the entire situation up at the very top. If we stop the whole situation right here, that's going to give us a piece of information that's going to allow for some problem solving, as we'll see in just a minute. But first, on to our velocities. So our velocity is given to us. It's launched at some angle relative to the ground or whatever horizontal surface we're dealing with. So we will have an initial velocity in the x, which will again equal v naught cosine theta. Whatever theta is, it's not going to be so obvious with this problem. And then in the y direction, we have v naught y equals v naught sine theta. If you're having trouble remembering cosine and sine, for a horizontal surface, we can say cosine. 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 Cosine on the x, sine on the y. All right. I said that we can stop the whole situation up at the top. What that means is as we're moving through our trajectory, we have this velocity in the x direction. That velocity in the x direction, if there's no air resistance, or if air resistance is negligible, which means it's so small we can ignore it, then we can say our acceleration in the x equals 0. That means our velocity in the x is not going to change. So our final velocity in the x will also equal v naught x. For the y direction, though, we do have a y component. And there's an acceleration that's pointed in the opposite direction. If we have an acceleration pointed in the opposite direction of our velocity, we're slowing down. So we're slowing down as we're in the y direction. So anywhere along this trajectory, our y velocity vector is decreasing. And as we get higher and higher, that y velocity vector is decreasing. This is not drawn to scale, but if it was, all of these white arrows would be exactly the same. At the very top, the only thing that exists is the white arrow, is the x velocity. So there's still a velocity in this direction. Meanwhile, gravity is accelerating it downward still. That doesn't mean that gravity stops working. There is a force acting down, which has the result of there being no vertical component of velocity at the maximum altitude of our trajectory. What that means to us in problem-solving terms is our final velocity in the y equals 0. So I'll add that over here. Final velocity in the y equals 0. We can use that to our advantage by using one of our equations. Let's say if we have Vf equals V naught, both in the y, plus AT. We have our acceleration in the y, right? Acceleration in the y equals -10. So when we plug in -10 meters per second squared here, we can now solve for time. We know that this equals 0 and this equals whatever number it gave us. Or just V naught sine theta if we're not actually dealing with numbers. Once we find time in the y, then we take that same exact time and we bring it over to the x to find whatever it is we need in the x. If we have x equals x naught plus v naught y t plus 1/2 at squared, the a in the x is 0, so all of that junk goes away. Our starting position is 0, which tells us our distance, or the range that it flies, is v naught x times t. Sorry for that typo. That's case 2. For case 3, we would use the quadratic formula to find time, and then from that, or you can just usually logic your way through this. Remember that we have parabolic motion right here, and then it drops whatever extra height. At that point, it would just be in free fall.